Hello again, everyone, and welcome back. 734, we're making our way through differential equations where we've talked about solving them and visually what that means. And now we're going to talk about graphing them, especially a little bit more complicated ones, by using a little, technique, you might call it, called slope fields. Okay. So I like to keep it the same examples to just build and get deeper into it. So first example we've been looking at is, let's say we have dy dx is equal to 2x. Okay, it's one that we've seen a lot, but it'll help you understand the main idea here. So we have dy dx. We know that this function here, we know what it looks like, but the idea is we're trying to get, the goal is what's your function y that it's describing. Okay, now by solving this, which we've done multiple times now, by separating variables and integrating each side, we get y equals x squared plus c. Okay. Now, if you remember what I've done in the past, is the idea is that y equals 2x, we know what that looks like. There's your dy dx. But the goal here is what's your function y. Now, notice we get y equals x squared plus c, which we know is a parabola. So it's going to look something like this. At any, there's a lot of different scenarios it can look like there. Because of the c, there's infinitely many, right? There's infinitely many functions with dy dx that's equal to 2x, as seen by my parabolas. Now, that's one way that we created this graph to help us visualize this. Now, what we could have also done is what's called a slope field, where say we weren't quite sure what the function y would look like, because maybe the integration is hard, so we just want a visual of it. What you can do too is to try to account for every possible scenario. Is remember that we're given dy dx equals 2x. We can use that to find the slope at every moment per se. And when I say moment here, I'm really talking about every coordinate x, y. And then that will help us piece together what the function y might be. So say we looked at x equals 0, right? If we looked at x equals, let's make a table here, x dy dx. If we looked at, say, x equals, well, let's even do this. -3, -2, -1, 0, 1, 2, 3. Pretty big table. Well, that's fine to do the 3s. Let's just do the 2s. All right. Well, x equals -2, then dy dx would be -4, because again, this was equal to 2x. So every value where x is -2, the slope is -4. And all I'm doing is a little slope line here, because again, and these are all parallel to each other, because every one of these values is x equals -2. So we know the slope at that moment, right? We know the slope at that moment. At x equals -1, the slope would be -2. So at -2, all of these, the slope would be 1. So it's a little bit flatter. Well, even my head, if you're wondering how I'm doing this, -4 I know is down 1, 2, 3, 4 over 1. So I'm just approximating the steepness there as if I were to continue it. -2, that's down, well, this should actually be a little bit steeper than what I'm making it. Down 2 over 1, down 2 over 1, etc. And these would look something like that. At x equals 0, notice the slope is 0. So at 0, the slope is 0 at all of these, which is just a horizontal line. At x equals 1, the slope would be 2. These are all the same. And at x equals 2, the slope would be 4, which is more steep. The first one's a bad one. And you can see that what we're trying to do is we're trying to basically create all possible, it's creating all possible solutions, f of x or y, whatever we've been using. And that's the same idea with the problem, it's just not connected. So then if we were given a known point, so say we were given a known point, which I think in the last video was f of 0 equals 3, f of 0 equals 3. Well, what we found out then was that implied that y was equal to x squared plus 3. So we know what that graph looks like, and on the slope field, we say, well, if we know f of 0 equals 3, 1, 2, 3, well, I'm going to change this up really quick, just so my graph looks. Let's do negative 3. So then it'd be x squared minus 3. So this point down here, at that top point. Then using our slope field, we can approximate what y is going to look like. Because again, the idea is what's our y? We can approximate that it's going to look something like this, following the slope field. Doesn't necessarily go through all those slopes, right? That's just saying at that moment what the slope is. So it's kind of tricky by hand to make this perfect. Okay. Let's look at another example, talking about these slope fields. And again, now let's do one a bit more complicated. Let's do dy dx is equal to y, which I know we've done. Want to keep with it. So if we look at dy dx equals y, now this one gets a little bit trickier. So let's see if we can visualize what it looks like. And then we'll match it to the differential. Now, there's two ways to make a slope field. I'll just mention that here. There's multiple ways to make a slope field. One way, which I'm going to do right here, is to use a table and plot points. Well, I guess you're not plotting points, and plot tangent lines, okay, or slopes. And then the other one is to solve for y and look at the infinitely many possibilities, which is kind of like what happened previously. Now this one assumes you know what the parent function y looks like. You know what the parent function y looks like. Like, for example, in the first one, when I did y equals x squared, well, I know x squared is a parabola, so that's how I knew it was x squared plus 3. If I didn't know what it was, this might be more difficult, in which the table was the better way to approach this here. All right, so let's say dy dx equals y, and you want to know, right, we want to know what function y dy dx equals y is describing. Okay. I think I misspelled that without an S. All right, so let's make a table. Erase that. And we'll do this. So let's do a table y dy dx. Let's look at some values here. We'll do -2 to 2 again. So if y equals -2, the slope is -2. So every y value of -2, which is right here, the slope is -2. So here's -2. So all these y values, slopes -2. Look like this. You can see that they're all parallel in a horizontal manner. -1, they'd all be -1. That looks like this, roughly, because again, in my head, I'm picturing going over 1, down 1. At 0, they're all going to have a slope of 0. So at 0, you can see this because I know I'm overlapping the x-axis there. At x equals 1, the slope is all 1. And at x equals 2, the slope there would all be 2, so it's getting steeper. There you go. And we can kind of see what it's looking like, because it looks like you're going to have a curve that's where 0 is your asymptote. This looks like an asymptote that the curve is approaching, and that's great. Now, that's us getting the slope field, and that would help us. Now let's get a solution to this. So let's solve for y and see what happens. So dy dx equals y. You have dy over y equals x, or dx, integrating both sides. we'd have that the natural log of y equals x plus that constant c. And raising both sides to e, we'd have e to the x. I'm just going to put that constant c in front, which again is the, well, I want to show you guys something actually. So in relation to last video, because I can give you a little preview of it. E to the x, and then that would be e to the c if you separate those, is equal to y, which again, we can call all this some number c. So we'll say y equals c e to the x. Okay. Now, sticking with the last video, let's say we know, let's say we have a known value, which is f of, what I say, 0 equals 10 in the last video. Okay. So what I talked about is if we plug 10 in, now my hint was plug in when after you solve for y. After you solve for y. And if we do that here, we would get 10. So if f of 0 equals 10, be 10 is equal to c times e to the 0, which implies 10 equals c. Thus, we got the equation y equals 10 e to the x. Now, I talked about how if you would have plugged it in sooner, like say we would have plugged it in at this step up here, we would have had natural log of 10 is equal to 0 plus c, which implies that c equals the natural log of 10. Now, I hope I didn't misconstrue it, but it's not necessarily wrong. But the idea is that if c equals natural log of 10, this is the value of c for this function y. It's not necessarily the value for this function y, because c, what happens here is in this function y equals c to x, we made c e to the c. So if we would have rewritten that as y equals e to the c e to the x, it would have been y equals e to the natural log of 10 e to the x, which is y equals 10 e to the x. So it's the same thing we got, but there's that extra little step there where we would have had to say e to the c rather than just c. And that's why if you follow my hint, you usually don't have to account for that in your final answer. You get a little bit quicker, okay? So visually, what's this mean now? So if your value is f of 0 equals 10, well, 10 is, way up here. Visually, I don't even know. Let's say f of 0 equals 10 is up here. But then what happens visually is this graph is going to look something like this. And there you go. And that's our differential. Well, that's us solving the differential for a particular solution y. Now, one thing I want to let you know, though, is I kind of skipped over something here when solving really quickly. And that's that when I rewrote this as y, remember how you could have gone a plus or minus when you get rid of the absolute value? So we really would have had y equals plus or minus c e to the x. Now, why does that matter? That matters because notice that on this graph visually, there was two possible scenarios. You could have had a graph above x equals 0, or you could have had a graph below. That known value gave away where this function lies. So since f is equals 10, then that implied that we were above the x-axis, thus making it y equals 10 e to the x. If it would have been f of 0 equals negative 10, then we would have had y equals negative 10 e to the x, in which the graph would have been below. Right? You cannot jump asymptotes when solving differentials. Okay. And really, you can't jump vertical asymptotes. But the idea here is that there's only one smooth curve that we know of, not two. So even though you might be thinking, wait, shouldn't it also be on bottom? We don't know because the only known value we had was f of 0 equals 10 there. Okay. Let's look at one more, and I'll remove that. Hopefully that looks a bit messy. Hopefully you followed that and didn't just jump the video. Because you would have jumped the video and be like, whoa, a lot going on there. That does not flow, and I get that. So hopefully you're following along. And then the last one, example 3, and then we're going to talk about a few connections here, is let's do the differential equation dy dx. Well, what if it was written as f prime of x equals xy? And I just say that because don't be tricked. F prime is just another way of saying dy dx. Okay, separating variables there, we'd have dy over y equals x dx. We integrate, and we'd have natural log of y is equal to x squared over 2 plus c. Raising both sides to e, we'd have e to the x squared over 2 plus c is equal to y. And technically the plus or minus there when we get rid of the absolute value. And thus, if I rewrite this as e to the x squared over 2, e to the c, I'll call all this just a constant c. And rewrite my final answer is y equals plus or minus c, e to the x squared over 2. Good. Okay. So say we wanted to know what the graph looks like. So what's the graph of y? Well, using method 1 of solving for y, let's see, use our graphing calculator here. Y equals e to the, put this in parentheses, x squared over 2. And then down below, I also want e to the e to the x squared over 2. So that's in parentheses. Okay, that looks good to me. If I graph this, you see that there you go. So there's a possible scenario. All right. So visually, you can see that one situation is like this. And I'm curious if I was just to put a c value in front of a number, let's say I put in a number 2, how that changes. 2 there. So 2 looks like it's just getting skinnier. Okay. So maybe it looks like this, where then I guess fractions would make it get wider. Okay. Similar up here. But that looks a bit messy, but those are all your possible solutions. That last one was bad. Let's do a slope field with the method 2 approach and analyze this a little bit with the table, that is. All right, so since it's x, y, we kind of have to make a bigger table. So let's go x, y. Let's see if I'm doing this right. I don't know if I am actually. Am I? So I don't even know what I'm doing. Let's go -2, -1, 0, 1, 2. And then our y values will do -2, -1, 0, 1, 2. Okay. So this is going to be interesting. I think I made my table kind of complicated, but no big deal. We'll work with it. So if we're at the point, say 0, 0, the slope there is 0. Right. And what I can also see from this equation technically is that if x is ever 0, these are all 0. So the inside here represents the derivative, the slope. So all x values, if x is 0, the slope is 0. And similarly, if y is 0, they're all 0. Okay. And let's see here. If we look at the point, say 1, 1. So 1, 1, you'd be at 1. And at 2, 2, well, 1, 1. And let's see, at 1, 2, at 1, 2, you'd be at a slope of 2, so it gets steeper. 1, 3, it'd be steeper even more. 1, 4 would be steeper even more. And similarly going down, and I'm not even using a table now, I'm sorry, I'm just working out in my head. At 1, -1, it'd be negative. So what am I doing? At 1, 1, it's that. I did at 1, 2, the slope is 2. Yeah, see, I don't even know if this is helping you see this in the table. I'm just trying to do it like you'll see it in the book. At 1, -1, it's -1, -2. Value here. That's how bad my table is. Yeah, it's okay. All right, at x equals 2, say we're at 2, 1, we would be at a slope of 2. At the slope of 2, 2, we'd be at a slope of 4. Gets steeper. So let me see, at 2, 2, 2, 1, we'd be at 2. At 2, 2, we'd have a slope of 4. And then that's pretty similar down here. It gets steeper. And I can already see, and you can see how it's matching this parabola because it's 0 and it's matching the parabola, which is good. The second method of finding all the individual points is working out. And I think if we just match that over on this side, it will be the same way. 2, -1, -2, -4. And up here, multiplying those would be at 2, 1. Again, I'm multiplying because it's x, y, -1, -2. So at -1, -2, well, I like going in this order. -1, 1, you'd have a slope of -1. -1, 2, you'd have a slope of -2. And it would get steeper. And then down here, -1, -1 would be a +1. And a +2, +3. And finally, we'd have 4, 2, 2 times -2, and -4. Okay. And -2, 1 would be -2. -2, 2 would be 4, in which actually a parallel along a diagonal here. There you go. In which that would help us approximate our solution. Now, notice that there's two possible scenarios here. There's the positive or negative. So that known value matters. That known value matters. Because there's typically only one particular solution given a known value. So say, for example, we were given here that f of 0 is equal to -2. So then if we plug that in, we would have y equals c e to the 0. Well, not y is -2, which implies that c equals -2. So then our answer here is y equals -2 e to the x squared over 2. So visually, that means that 0, -2, there's a point. What this curve looks like is something like this. And that's your answer here. That's the solution to this differential. Nothing up top because of the known value. Okay. Now, just some things I want you to observe to help you with the values is some observations to make note of that I just did. And by observations, as if you haven't been making observations, right? Just kidding. Additional observations to be made. Okay. In the very first one I gave you, in example 1, it was dy dx is equal to, what was it now? 2x. And notice that in this problem here, when we had dy dx equals 2x, here it is here, that the slopes were the same along a vertical line, right? So the slopes were parallel vertically. And you might think that's because given the x value, which is your row or your column visually, x equals 0 is like your whole value is 0, all y values follow suit. And then what happened in example 2 is that I gave you dy dx equals y, which was this function here. And notice that the slopes were parallel in a horizontal manner, right? So that means the slopes were parallel. Slopes were parallel horizontally. As again, it was, if you know the y coordinate, it's the same for all as x changes. Okay. And then this third example, notice that there's really no parallel slopes here. The slopes were the same at a diagonal, but you wouldn't call those lines parallel because they're on top of each other. So example 3, which was dy dx equals xy, there was no parallel slopes. Now, the additional observation to be made here is notice that vertically is when your differential is when dy dx is in terms of x only. And that will be the case. If you ever get a differential in terms of x, we know that there's going to be, the slopes will be the same vertically. In this case, dy dx, if it's in terms of y, that's when this situation will happen, where the slopes will be the same parallel, or horizontally, they'll be parallel horizontally. And lastly, this is if dy dx is in terms of both x and y. So there it is, slope fields with a little bit more going on, and it might have felt long or maybe a bit tricky, but if you try it yourself, I think and I hope that it makes a little bit more sense to you. Okay. If you have questions, write them down. Just make sure you ask, and I can do my best to clear them up. All right. Bye-bye.